and thank you for the opportunity to be able to present my work in this conference. So my name is Ratnesh and I'm a PhD student in Professor Sheila Nikurmaik's group at OIS Japan. And today I'll be presenting our work where we used a machine learning approach to improve the number of rubidium-87 atoms trapped in an evanescent dipole trap around an optical nanofiber. This work is done in collaboration with the Professor P.K. Lam's group from Center of Quantum Computation and Quantum Communication Technologies at Australian National University. So, and we use a machine learning approach very similar to what uh, Professor P.K. Lamb's group used before in order to optimize the optical depth in their system, which I will talk about in the further slides. So why are we interested in such a system is because in the small mode volume of the evanescent field, with the high intensity of the field, we can have a strong interaction with the rubidium atoms or other atoms, any kind of atoms, strong interactions, and potentially in the optical nanofiber, since the evanescent field is over a longer length of over the entire length of the nanofiber, we can have potentially interactions with multiple atoms, so leading to collective effects and studying, which is basically highly desirable for any kind of larger scale quantum communication schemes. So there have been few talks about optical nanofibers in this session. I'll just briefly talk about optical nanofiber, describe the optical nanofiber, and then jump on to talk about the important features that are crucial for this work. So what is an optical nanofiber? As you have been hearing, the optical nanofiber is basically a subwavelength diameter nanofiber in this region here, which is produced by heating and pulling a standard optical fiber in such a way that the light coupled through the standard optical fiber region here is losslessly coupled through this taper region into the mode of the nanofiber here, with a distinct difference here now that now here outside the fiber, there is a significant portion of the power traveling outside the fiber in the form of the evanescent field, which can then interact with the surrounding medium, and in our case, with the rubidium atoms. So what in our case, if you see the evanescent field, it depends on the polarization, the mode, and the wavelength of the light propagating through the nanofiber and the diameter of the nanofiber. So for a fixed wavelength, if you see as the diameter of the nanofiber decreases, more and more light propagates outward outside the nanofiber, and there is a larger penetration depth. What it also means is if you have a fixed diameter, the longer wavelength decays further away from the nanofiber surface, while a shorter wavelength decays much quicker. And if you look the intensity field around the nanofiber, you will see that there is a high intensity and then there is a low intensity. And then again, there is a high intensity region around the nanofiber as you go around the nanofiber. And this depends on basically the um, polarization of the field propagating through. We are restricting, for our case, we are restricting ourselves to the fundamental mode of the fiber, which is basically the HE11 kind of a mode, which has pretty much Gaussian-like of an envelope inside. So with these two features that we have the azimuthal variation and different radial decay length of the red and the blue light, basically, what we can create is a potential minima of 1D lattice around the nanofiber using a scheme proposed where a red and the blue detune light from the resonance. In our case, we are using rubidium 87. So 780 is our transition, 780 nanometer is the transition, and we are using 1064 nanometer as the red and 762 nanometer as the blue light, where if we send these red and blue, the red will tries to pull the atom close to the atom, close to the nanofiber surface, while blue pushes it away, and thereby with a right balance of power, and since they have different decay length, we can create a potential minima few hundred nanometers away like this from the surface of the nanofiber. So we have here, we show the calculation for potential calculation for the 1064 nanometer and 762 nanometer blue light that we use, and we get a potential minima of around 350 microkelvin and at a distance of roughly 250 nanometer away from the surface of the fiber. And this is along the radial direction. That is, if you look at the surface, you see a potential minima around this. And then this is an actual, we can have a standing wave potential if we use two counter propagating red detuned light. So in this case, we have an axial localization as well, like this, a regular interval potential minima, and this is what is shown in the, and the wavelength that we used is the 1064 nanometer for red and 762 nanometer for the blue. This shows here the schematic of our experimental setup. Here we have a nanofiber installed within a vacuum chamber, and these lights show here basically the laser cooling beams, which is the first step to get a cold cloud of atoms around the nanofiber within the magneto-optical trap. And then these red light here forms the standing wave potential, which is the red detuned light beams. And then this blue is basically sent through in one direction, pushing away the atoms. So the atoms can be trapped in the standing wave potential created by the red. This and this here we show a probe light, which is probe light beam, which is used to then observe the transmission, or in this case absorption of the system. Once the trap is loaded, we see the absorption using a probe light which is resonant at 780 nanometer T2 line of rubidium, and then is observed filtered through the VBG, which is a volume Bragg grating. This is used because we want to detect roughly a picowatt level of probe power, while there the stray light of microwatt presence due to these trapping field lights. Such kind of system has been used before in multiple experiment, including the memory experiment, where they have stored a fiber guided light in the nanofiber and stored it in a trapped ensemble of cesium cold atoms around the nanofiber in a similar 1D lattice. And then they have observed a collective quantum spin states in an ensemble of similar trapped atoms. And very recently, they have created a single collective excitation in such an array, and where they have generated a Dickey kind of a state in one of the experiments in 2019. However, all these experiments are done with cesium, and here we see typical absorption profile in the case of a cesium experiment, which was done in Arno Reuschen-Beutel group in Vienna, and the another one is with the rubidium. The experiment was done in University of Maryland group, Steve Ralston group. So here, if you see, in the case of cesium, they have been able to trap 2,000 atoms, while in the case of rubidium, they have only 302 trapped atoms. The difference comes from the fact, as you can also see in the spectrum behavior, the spectrum looks very asymmetric compared to that of cesium. And this comes from the difference in the cesium and rubidium, that in the case of rubidium has very high vector polarizability. What it means is at different levels will shift differently depending on the polarization of the trapping potential. And since in the case of evanescent field, we have a significant amount of longitudinal electric field, which comes from the fact that we have a radially decaying field profile, which leads to a longitudinal field that creates a vector shift in the case of rubidium much more, and makes this line profile asymmetric. So what we want to see is, in our case, can we make this better in case of rubidium? Can we improve this number of trapped atoms using a machine learning approach? So first we get a trap, and in our experimental cycle, the schematic looks like this, where we have a 2-second cycle, in which first we have a Mott cycle, which represents the phase in which we have thermal cloud first cooled down via laser cooling and loaded onto a magneto-optical trap. And so that we have something like this, a cold cloud, which is centered roughly around the nanofiber. This yellow line is added on top to represent the position of the nanofiber. And here the temperature of the cloud is roughly around 100 to 120 microkelvin. And then in the next step, the molasses phase, remember the transition scheme. In case of rubidium 87, we have a cooling transition F equal to 2 to F prime equal to 3. The cooling beam is kept for a little bit red detuned in order for the laser cooling to work. So in the molasses phase, what happens is we turn off the magnetic field. So there is no more localization, no more trapping, and the cold cloud, which was 120 microkelvin to start with, start to expand. And then when start to expand, and when we reduce this power of cooling beam and further detune it further from the cooling transition, the temperature is also reduced for the cloud, which is, and by the end of the molasses phase, we get a cloud which is roughly 40 microkelvin in temperature. And also in this period, in this phase, while the cloud is expanding and further cooling it down, since the trapping beams were always on, kept on through the systems, this dipole trapping beam, which is different from the magneto-optical trap, this dipole lattice, some of the atoms are then captured into this potential minima created by the dipole trap. Now, at the end of this phase, we turn on the probe beam, we turn off all the cooling beam, and all magnetic field was already turned off by the end of this phase. So there are trapped atoms in there is just the trapping field which creates this dipole lattice and some of the atoms which were captured in this uh, trapping field. So then in the measurement window, we turn on the probe beam, which is resonant to this F equal to 2 to F prime equal to 3 transition. And then we observe the transmission of we measure the transmission of that probe. And if you see here, in the beginning, there is probably much more atom. So most of the probe is absorbed and there is very little transmission of the probe. And as the time passes, the atoms are lost from the trap, and so the more and more probe can come through the nanofiber and thereby finally reaching the full transmission. So this indicates the number of atoms that are trapped in the system, trapped in such kind of a dipole trap. So using this, we can measure the absorption spectra. So if we see the absorption, that one shows here is the dipole trap where there is no dipole trap, and here where there was a dipole trap on. So what we have is, in the case of dipole trap, and note that the only difference is the polarization. With the polarization mismatch of the counter propagating red field, we can turn on and turn off the dipole trap while keeping the same amount of power going through the nanofiber. So when there is no dipole trap, we see a very familiar Lorentzian kind of absorption, which essentially comes from the atoms, cloud of atoms moving through around the nanofiber. While if we see the trapped case, we see a sudden dip, which is like the increase in the absorption. As you can see, it's the maximum is around 0.2 here, while in this case, it's almost reaching below 0.1 and reaching 0. And also this is further broadened, which is an indication of more number of atoms in the system trapped. Now with this, and we have estimated the number of atoms trapped in such a scenario by taking into account the temperature of the atom and the potential profile of the trap volume. And we found that we had 450 atoms trapped in such a system. Now what we want to see is, using a machine learning optimization, can we improve this number even further? So we use a machine learning scheme which is very similar to the one used by the ANU group, Australian National University group, before in their experiment, where they tried to improve the optical depth in their system. So what they have is again a magneto-optically trapped cold cloud of atoms, which is then transiently compressed along the probe direction using the trapping, repump, and Mott coil experimental controls. It's such that with this compression, there is more atoms along the probe and thereby increasing the absorption and therefore the optical depth of the system. And then this optical depth, which is observed for a particular experimental control, is sent to a set of neural networks where the cost function typically is what a neural network is designed to typically optimize a cost function. What the cost function is, it depends on the experiment. In this experiment, for example, cost function is basically the inverse of the optical depth. So as the optical depth increases, cost function decreases, and the neural network is being trained to reduce the cost function using a BFGS algorithm. So, and it then predicts the new set of parameters which would further reduce the cost function on the basis of this run and the trained over the previous set of runs. This here just shows the different parameters, experimental parameters they have, and how they function and how, what kind of result, like in the case of what kind of optical depth they produce. And then this new set of parameters is sent to the experimental control and the cycle is repeated. And the cycle is repeated until the system cannot find better solution for the cost function or the system is optimized. So what we use in our case, we have the same kind of experimental cycle where magnetic fields are one set of parameter. Magnetic field controls the localization of this cold cloud around the nanofiber, because with the gradient and the compensation field, we can move this cloud around and how well and we can center it better on the nanofiber. And then in the molasses phase, we have cooling beam detuning, power, repump power, and the time of this section and trapping power. So these further affect the temperature of the cloud, and the trapping power here is basically which changes the potential profile of the trapping for the molasses period. And our assumption was if we slowly change the trapping potential and make it deeper during the time of molasses, it will help, it will effectively better the loading process. And what we see in the measurement, it shows the one profile before optimization and another after optimization. This is again the transmission of the probe over time. And if you see before optimization, the probe quickly goes up to full transmission. And while in the case of after machine optimization, the transmission is further reduced, which means the absorption is increased, which basically indicates there are more atoms in the system trapped in the system. In our case, the cost was very cost function. As I described earlier, the neural network is designed and trained to reduce the cost function. So in our case, cost function we chose as the average transmission, what we see in this. So if we decrease the average transmission, then that means there are more and more atoms in the system. And machine learning tries to decrease this average transmission over different cycle of runs. And this is what shows a typical run of a machine learning. So over each iteration, machine learning tries to find parameters so that it can reduce the cost function, basically reduce the average transmission, which also means increase the number of atoms. And here what you see is a slight running away. Basically it is trying to find, so once it optimizes and it can't find better solution, machine learning tries to see different parameters, parameter what is it called, parameter landscape, and tries to find a solution elsewhere. And if it doesn't find it, it comes back and tries to keep improving the cost function. So with this kind of setup, so first thing what we thought is perhaps this. So as I said, initially the cloud was 120 microkelvin roughly, and then after the molasses phase, it is around 40 microkelvin, within which also it was trapped. So our first assumption was, and we wanted to see, is if this temperature is affected and it is further reduced, which has helped facilitated the better loading of the trap. So we wanted to check the temperature. So the upper row and the lower row shows the cloud expansion. So cloud image at different time delays. So what we want to see is the cloud expansion, and this cloud expansion gives us what is the temperature of the cloud. So from here, we see they had roughly very similar kind of cloud expansion. And when we calculated, it turned out they're both very similar, roughly around 40 microkelvin. So there was no such impact on the cloud. But if you look closely in the upper row, the cloud is little off-centered, while the cloud is much better localized onto the nanofiber in the case when the machine learning has optimized it. So what we found is that the localization of the position of the cloud was much more significant in the case for the trap loading than the temperature itself. Or the temperature was already in the better position. And I would like to end my talk by showing you the final result in our case. So the first is where it was before the machine learning, and this is done after the machine learning. You can see that before the machine learning, it's around 0.1 or something, but in the after machine learning, the absorption is increased further and the transmission is almost reaching zero. And also this broad end kind of a structure, when we estimate the number of atoms using the similar kind of calculation what we did before, taking into account the trap volume and the temperature of the atoms, what we found is 800 atoms in this second case, which is roughly around 70-75% increase. So in summary, what we show is ONF offer huge advantage for applications in quantum technologies. Atoms can be trapped using such a two-color um, Faraday tuned light, and machine optimization can be used to improve the number of trapped atoms near the nanofiber. In our case, we observed an increase by 70%, 75%. Thank you so much.
Thank you. Yes, so we can take some questions. So first, I wonder when you're trapping 400 or 800 atoms, and the signals are not entirely from the array, right? I mean, there are other atoms around, like in the clouds, right?
Mhm.
So, so can you sort of exclude or distinguish the contributions from the arrays and other from other atoms not trapped or like around?
So if you remember from Professor Sheila's talk, she said like at any time there are roughly 8 to 10 atoms in the cloud around the nanofiber, right?
Yes.
That's very little, first of all. And since we have turned off the trapping already
Yes.
before the measurement, and we are doing this measurement after the molasses phase,
I
there
see.
is very little of these stray atoms around the nanofiber, because you can imagine the absorption that is happening with the atoms that are very close to the nanofiber, right?
Okay.
A few hundred nanometer, and had to fall in the evanescent field region of the probe field, right?
Okay.
So there is very little of the stray such kind of atoms effect from such kind of
I
atoms
see.
in case of the absorption.
Okay. So I can really assume that you're forming an array of the atoms, or you're just tightening up your traps around the fibers. Is it like a realistic array, like equidistant atomic array, or
So the potential profile that, so we are assuming that atoms are trapped at the, I mean, not assuming, but atoms can only be trapped into these trap volumes that is
yes,
created, right?
yes,
So, and there can be some atoms which is moving inside, in and out of the trap,
I
perhaps,
see.
and
Okay.
we have not taken that into account. But for the most of the absorption measurement that we do, like these are the only atoms that will play any role into the absorption that
Mm-hmm.
we measure.
Okay.
Yeah.
Okay, Dr. Chen.
I'm wondering, is this machine learning optimization quite robust in day by day run? I mean, you can get pretty much about the same results day by day.
Yeah, so in our case, what we found that the parameter that was predicted by the machine learning has been quite robust, and we can use it for several days after that, unless we change the system or something happened to the system.
Okay.
Okay. Any more questions? Okay.
So I'm curious about that. If you load a lot of atoms in the dipole trap, then is there any kinds of collective effects so that if a lot of atoms are covering with nanofiber together, then maybe the decaying rate becomes faster because something like super radiance. So that if you use the average transmission, it might not be a very it might not loyalty response to the total atom number. So I'm just curious about
Yeah,
is there any
that's true. Actually, our motivation comes from the fact that we wanted to see collective effects, like for mixing, for example, in such kind of a system, and that's why we wanted to create such a increase the number of atoms in such a trap system. But we haven't done any measurement to confirm that, or see, we haven't seen any kind of a super radiance or kind of effect.
Okay, thank you.
Any more question? Okay.